This week's lab involves designing a 3-bit finite state machine based counter as well as a sequence detector using a finite state machine. So this will look very familiar to the lecture videos that you've watched. For the 3-bit finite state machine based counter, it's very similar to example 2A that you watched in the videos. So FSM example 2A and 2B explains how to design a specific counter using an FSM. And you will be doing that in your lab and implementing that in VHDL. And if you will also recall, lecture 14F goes over how to implement FSMs in VHDL. So my suggestion is have your textbook open and start with using something like the FSM on page 585 as your template. So this is you can use this as a generic FSM and modify the reset signals and the mealy and more outputs and number of states as you see fit. So as explained in the 14F video, once you have drawn your FSM state diagram, it's rather easy to translate this into VHDL. So that is the main focus of the first lab or first experiment. And similar to your T flip-flop counter that you designed, in your overall VHDL you'll be creating one entity, which is this big box that's going to hold all your components. It's going to hold the 7-segment decoder, which you've already used, the clock divider, which you've already used, and then the 3-bit counter that you'll be creating based on the state diagram. So that's your experiment 15. For experiment 16, you're going to be creating a sequence detector. And the sequence detector, again, it's very similar to the lecture and homework problems. So if you want to go back and review sequence detectors in both the Moore and Mealy styles, you can watch the lecture videos. And you're just going to be creating that within your Nexus board. And so what I'd like is a write-up for both of these, but you only have to demo experiment 16 and be sure to include an ISIM waveform for experiment 15 to verify that it is indeed working. Now I wanted to mention some more about the sequence detector. Not only have we provided the clock divider module, but you'll see you're going to include some other components as well. You're going to be including this sequence driver module, and also instead of the 7-segment decoder, you're going to include this BC decoder, which is provided for you. So if you look at your lab assignment, you can see there's the clock divider. The 7-segment is for experiment 15, but then the sequence driver and the BC decoder are both for experiment 16. Now, what do these files do? Well, the sequence driver, let's go ahead and open that up. If you look at this, basically what it's doing is it's taking the 8 bits on the switches and sending out one of those 8 bits one at a time with each clock pulse. So this is what is known as a parallel to serial converter, because it's parallel in a sense that you have 8 bits coming in on this switches bus all at once, but you only want to output, so you see your input is 8 bits, but you only want to output one of them at a time, serially, which is a single bit here, X as your output. And so as you can see here what's happening, with the rising edge of the clock, we are just adding 1 to a counter, and we're counting up until 8. So what this is doing is if the counter is at 0, we're going to select the least significant switch sub 0. So it's sending X just a single bit. When the counter is a 1, which comes at the next clock edge, then we'll send out the next bit on the switches, etc., etc. So if it's 2, then you send out the next bit. This is just for a visual check for you, and as you can see, if you're sending out the least significant bit, which is 000, you're going to just turn on the least significant LED. If you're sending out the next least significant bit, you turn on the LED that's next to it. If you're sending out the most significant bit, you're going to be turning on the leftmost LED. So this is just for a visual check of this sequence driver. Okay, so this is taking your 8 bits of the switches and sending them out one at a time to then be sent to your FSM. So as you can see, your output of the sequence driver will be connected to your input of your FSM, which you are creating. The clock for the FSM is the slower clock coming out of the clock divider, which is also driving this sequence driver, so you can see how that's connected. Now this BC decoder is very similar to your 7-segment decoder, but instead of it putting out numbers, it's putting out a message. And some of the students who have done this lab in the past like to call it the cool crap lab, because if you detect your sequence, this decoder will display the word cool, and if you don't detect the sequence, this decoder will display the word crap. So if you look at the BC decoder, you can see that's what's going on. Your input is the clock, and the Z, which is the output of your sequence driver, which is the output of your FSM, that's telling you whether you have detected the sequence or not. And then your outputs are the typical anodes and cathodes for the 7-segment display. So as you can see here, we are displaying different segment codes to give us a cool, C-O-O-L, or a crap. And that depends on whether Z is a 1 or a 0. So if Z is a 1, then we are setting the digits that we're going to be displaying to represent the cool, which are 0 through 3. As you can see, that matches these 0 through 3 up here. And if we don't detect, which is when Z is a 1, we're going to set the digits to display crap. So as you can see, that's 4 through 7, and that's the same as 4 through 7 up here to select the right segments. So that's what that file is doing, and I think this is a pretty fun lab and gives you also other ideas of how to use the 7-segment display to show something other than numbers.